This is the third PowerPoint C, the video that goes with that. It's at the lecture that we had in class for that day. We're starting with resonance, and resonance, the easiest way to describe that is if a molecule can be drawn more than one way, or if it can exist in more than one form, then it's going to be in those multiple different forms. And when you think of resonating, something that, like if you strum a guitar, it resonates in the wood and makes the music a little louder. You think of resonating as alternating back and forth or vibrating. Well, that's to some degree. It's oversimplifying because it really doesn't clunky vibrate back and forth, but it does move, the electrons move smoothly into the multiple forms that it can exist as. On the notes here, you see that there are two legs on NO2 minus, and the two legs, one of them is a double bond, one's single. The double bond is on the right, then the double bond's on the left. And to show the resonance for this, you would show the form, the two forms, and an arrow in between that shows that they're alternating back and forth between the two forms. That's resonance. Resonance gives stability. So it's important you understand that, because there are some forms where there may be 7 electrons on an atom in one, and in the next form, that side gets 8. So what it does is makes up for maybe just having 7, because part of the time it gets 8. So resonance increases stability. There are going to be 6 exceptions that we'll talk about in this chapter, and I will ask you 1 or 2 of those on the test and 1 or 2 on the quiz. So just maybe make some flashcards. Go over, here's what you don't expect to happen on these 6, so that you will expect that to happen. So first of all, phosphorus and sulfur. They're in the third row. They're a little bit bigger ring, and sometimes they will accept more than 8 electrons. And for phosphorus, easiest way to think about that is to do, if I ask you to show the exception for phosphorus, show the 5 electrons around it. And if it were in a rich environment with hydrogen or one of the halogens, those are the exceptions that I'll ask you. Notice it can be fluorine, chlorine, could be bromine or iodine or hydrogen. If it were in a hydrogen-rich environment, the hydrogens come in and share because they all want 2 electrons. Notice that each hydrogen is now stable and happy because it has 2 electrons. But the phosphorus, before it realized it, all of a sudden, boom, it's got 10 valence electrons. And it's an exception. It does allow this. It's a stable form that exists. So this is pH5. And what I'll do is I'll just say, show the dot diagram for pH5. Or I'll ask you to show the exception with phosphorus and hydrogen, or phosphorus and chlorine, or phosphorus and iodine. And it has 10 valence electrons. Sulfur, pretty much the same thing with sulfur, except it's got 6 valence electrons. So there's sulfur, 1, 2, 3, 4, 5, 6, and it will take 12 electrons and have an extended octet. So it will have 12 where you'd expect it to stop at 8. So we have 2 of the exceptions. Those are in the third row, bigger rings, so they can extend the octet. In the second row, think of the analogy here of a little dish, and let's say you're feeding 10 puppies, and you've got a little dish of milk. They can't all get in there. If you had a big dish, they could. Well, it's the same thing with these electrons. On the third row and beyond, there can be extended octets. So the bigger rings, the third and fourth rows, can do the extended octet. The second row is like the small dish. It can't fit all the puppies around at the same time. It can do a short octet. In other words, it can be short 2 and have 6. And this is a really important model because we're going to talk about the shapes again. We've talked about them already with VSEPR, but we're going to talk about the shapes. And this is a shape called a trigonal planar shape. And it would be boron with 1, 2, 3 electrons. And the same thing happens that happened with the phosphorus and sulfur, except it's not 8 and it's not more than 8. It's less than 8. It ends up being a outer shell of 6. And boron allows this to happen. It's actually not its most stable form, but it will exist this way. And because there's no central unshared pair, the easiest way for this to exist is a planar molecule, all in the same plane. This is called trigonal planar, where this is boron, these are hydrogens. Trigonal planar. So when we talk about BH3 and its shape, it's one of the few examples of the trigonal planar that y'all will see. There are some others, but make sure you know that that one's trigonal planar, because I believe on the quiz or the test, I ask you what the shape of a BH3 molecule is. Trigonal planar. You should know that. Okay? So those are some of the exceptions. On the next page, I actually pulled that off of a diagram, and they had this diagram not drawn correctly for the final form. Here's one more of our exceptions. Okay? So remember, a double bond has 4 electrons. Each stick or bond has 2. So 1, 2, 3, 4, 5, 6, 7, 8. Oxygen's good here. 1, 2, 3, 4, 5, 6, 7. Nitrogen only has 7. Now, if it can, it will go out and get an electron from somewhere and become a polyatomic ion. It's not one we have on our list, NO 1-, but it is a candidate for being a polyatomic ion. If it can't get an electron, it exists like this. Why does it exist like this? Because it has a resonance form of N with 8 and oxygen with 7. So it alternates back and forth between these two forms, and it does so quickly that the oxygen and nitrogen don't really feel like they're short in electrons. So that works out for them. And that's another exception. So that gives us 4 of our 6. So VSEPR, you should know that that's valence shell electron pair repulsion. In other words, electrons don't like each other. They repel each other. So this determines the shape of what we expect our molecules to be in. And to remember these shapes, the thing I tell you is use a tetrahedral molecule, and let's work our way from tetrahedral down through bent triatomic. So here's tetrahedral. No matter how I set this, and you could try it with a model, every way it's identical. And the reason is because the electrons are pushing equidistant in every direction, 3-dimensionally. And that's what they do. That's the idea of VSEPR. This, with 1, 2, 3, 4 around a central atom, is tetrahedral. Well, let's take one off, and now we have something that only has 3 atoms around a central one, and this, again, has the same shape because that pair of electrons is still pushing the other electrons. So it pushes them down, and we end up with a pyramidal shape. Well, we take off one more atom, and now we end up with the shape of water, which is bent triatomic. It still basically is that same tetrahedral model, but we don't have atoms on these two, and we name the shape based upon where the atoms are. So here we have bent triatomic because there's 2 unshared pairs on top. So you can see that those 2 unshared pairs are causing it to bent triatomic. So you can see how we went through several of these shapes based upon just that one alone. Now, a couple of the other shapes, of course, the easy one, linear. You should always say how many atoms are in it. Diatomic linear would be 2 atoms, and triatomic linear would be 3. And that covers probably at least 2/3 of the models that you will draw or see and be asked to name the shapes for. The other one, like I said, is this trigonal planar that we drew a while ago for BH3, BF3, BI3. When boron's in the center and it has 3 legs, it's trigonal planar. So if you know those shapes that we just went over, I could say, I can't remember another one of the shapes being used, but 90% at least of what you see in here will be those shapes that we just mentioned. All right, so we're going to talk about electronegativity and polarity. So far, you've been able to use the stair step and say ion both sides, ionic, and if not, if they're both nonmetals, then it's molecular. Well, we're going to tweak that a little bit because there are some exceptions, probably about, it works for 90% of what we deal with, but there are some exceptions where we consider something to be molecular that might actually cross the stair step and be a metal and a nonmetal. So we have a rule that deals with the electronegativities. Remember, that's what the whole thing's about. If the electronegativities are widely separated, well, then one of them is going to steal the electrons. But if the electronegativities are closer, then it's a tug of war that maybe they don't win, and there is a number that we assign to that, and that's what we're going to deal with right now. So you should have an electronegativity chart in front of you as we go through this. The electronegativity charts are going to be on your possibly useful page, and if you don't have one, come get a periodic table at class, and on this chart that we're dealing with, right here is where your electronegativity is going to be on your possibly useful page. You remember the bond energies, that's here, electronegativities right here in the center. So electronegativity is how much one atom pulls at its neighbor's electrons. So we have a quantitative value. We are going to have 2 atoms on each side of a bond, and only ever 2. We don't ever look at like 4 or 5 atoms at one time. You pick 2 atoms, and we're looking at the bond in between. If there's 3 or 4 bonds in a compound, that's fine. You look at them individually, but we look at one bond. So how do we figure the difference in electronegativities of the 2 atoms? You write the 2 numbers down, take big minus small, that's the difference, and it's like absolute value. So the difference of the electronegativities, we're going to take that value to this chart and figure out, is it covalent, is it ionic? And there's actually 2 more steps here. We have 2 types of covalent bonds. One of them is called nonpolar covalent, where they're very, very, very close. Things like N2, they're the same, right? So there's going to be 0 difference. Those are nonpolar covalent. That means they don't have a plus and minus N. The bigger difference there is, the more polar the molecule, and we have that boundary. So you look on your little chart here, 0 to 0.399999 on the difference is nonpolar covalent. What if it's 4 to 1.69999? That would be polar covalent. So the easiest way to remember this is if you can remember the middle, which is 0.4 to right under 1.7, and then if it's over, if it's 1.7 or over, it's ionic. If it's less than 0.4, then it's nonpolar covalent. The middle slot would be polar covalent. So on the test, I'm going to give you a bond and say, what kind of bond is this? First step, look up the 2 electronegativities. Subtract big minus small, see where it fits in on the table, and that's your answer. Okay? So analyze one bond at a time, 2 atoms only. If you add MgCl2, don't think you're going to double the Cls because there's 2 of them. You're only looking at one bond, ever. So there's only ever 2 numbers to subtract. If you figure one bond, it's MgCl2. You figure one bond is polar covalent, well then the other is polar covalent too because they're identical. Because you've got Mg with 2 Cls on 2 legs. So what I recommend, and you're not going to get this and you're possibly useful, what I recommend is that you remember 0.4 to 1.7, just short of 1.7. That's your polar covalent. Below 0.4 is nonpolar, and above 1.7 is ionic. So that gives you the the chart, just if you can remember the in-between, that'll help you. All right, so we talked about polar bonds. Now we're going to talk about polar molecules, and if you have a polar bond, you can have a polar molecule, but it doesn't automatically make it a polar molecule. You have to have two conditions. One, polar bonds, and second, you need to have a molecule shape that gives two charged ends. So if you had two atoms and it was a polar bond, then it's a polar molecule because you've got a plus and minus end. But if you have something like methane, which is nonpolar, and this is one of the ones on the quiz if I remember right, that you have a C in the middle, H is all the way around. There's not more than one end out there. All there are H's. Every end's the same. Something like CO2. Both ends are O's. Nonpolar, because you have to have two different ends. Now, one thing that is a little tricky is that a bent molecule can be polar, like water, where you have H, O, H. Subtract those and you'll see that there's a difference that makes that bond polar. This end is plus and that end is minus, and there's unshared electrons there. Because it's bent, we consider the O to be the minus end and the H's to be the plus end. So water is a polar molecule. Methane, CH4, not polar. CO2, not polar. So what you need to remember here, maybe make some flashcards with polar and nonpolar, but again, draw the shape, draw the molecule, and then figure out, is it a polar bond? If it's not a polar bond, you know right away it's not going to be a polar molecule. If it's got polar bonds and it has a shape that gives you two ends, one end is plus, one end is minus, then it's a polar molecule. And it's a different question from polar bond. It's kind of like the next step. Okay, so make sure that you review over that, understand what polar molecules and polar bonds are. So we end up here with network solids, and network solid is a molecule that is a molecular compound that's a crystal. You don't have very many of those. Remember, all the ionic compounds were crystals. This is a molecular compound that's a crystal. And we have an example of this, the diamond. And this is a network solid. Diamond is a network solid. There's also a silicon version of this, that silicon and carbon are in the same rows, and it's connected three-dimensionally. Okay, very, very strong. Very high melting points. It actually just kind of explodes. It doesn't really melt. It just self-destructs because all the forces start torquing and the molecule breaks apart. But very high melting point, which is not the norm for molecular compounds. So if you're asked something about an unusual molecular compound that has a crystal, network solid. So that finishes up this set of notes. And work through your review. If you missed something on this, you could rewind, start over, try to go back and catch things that you missed. We'll have one more short section of notes to finish the chapter, and work your practice problems, work your review, and study hard. Good luck.